in here. Okay, so welcome back. So last time we talked about tissue types, and this time we're going to look at how those tissue types work together to form an organ, so it's the skin. Right? So every organ is actually made of multiple different tissue types that work together. So one of the things you'll kind of read about in the textbook, if you read the textbook, is this idea of levels of organization. So if we start, so ignore this for now. So the smallest levels we have atoms. They combine to form molecules, right? Those molecules combine to form the organelles and other parts of our cells. Similar cells work together to form tissues. Multiple different tissue types work together to form organs. Multiple different organs combine to form organ systems, and then all those organ systems together form an organism. So I am an organism, you are an organism, my pet cat is an organism. The plant under the cell is an organism, right? Composed of all these different organ systems working together. So in the human body, these are our organ systems. And so this is kind of roughly how we're approaching most of the rest of the semester, is going kind of organ system by organ system through these different things that work together to form the organism, which is your cell, right? So we'll do muscular system, skeletal system, nervous system. So each one of these is an organ system, multiple organs working together. Interestingly, when it comes to your muscles, each individual muscle is its own organ. So my biceps brachii is its own organ, my triceps brachii is its own organ, right? Skeletal system, each individual bone is considered its own organ, so they all work together to make the skeleton. Nervous system, each nerve, plus the spinal cord, plus the brain. The endocrine system is a system of glands that make hormones. Hormones are chemical messengers that travel through the bloodstream, and they're a way of communicating from one part of the body to another. We're going to touch on those a little bit later today. The cardiovascular system is the heart and all the blood vessels. The integumentary system is the skin and its accessory organs, which we'll talk about today. Lymphatic system, so all the little lymph vessels, and there's also a few other organs that contribute to that. Respiratory system would be your lungs, your trachea, which is your windpipe, and the upper respiratory system like that. Tissues in your nose that I've been swallowing a lot lately. Digestive system, of course, your throat, esophagus, stomach, all the intestines, liver, gallbladder. Urinary system is the kidneys and the bladder, and then, of course, your reproductive system. So we're going to do a tour through most of these over the course of the rest of the semester. Okay? So don't feel like you have to memorize anything about them right now. We're just going to give you an overview. All right. So we're going to start with the integumentary system, our skin and its accessories. Okay? So when we say integumentary system, that's what we're talking about, the skin plus its accessory organs. So skin is pretty cool. So it's actually one of our largest organs. So our surface area, like if you skin me and then let it all out, right? So about 1.8 square meters, which is quite a lot, more than 19 square feet. And it's 15% of your total body weight, which anybody who has skinned a deer and handled that hide is very familiar, right? It's pretty heavy. So it's a substantial organ. It's really quite large. And it does lots of cool things for us. So now I want you to kind of take a moment and try to think, what are some functions of the skin? What does the skin actually do for us? So take just about 5 seconds, try to come up with as many things as you can.
It produces sweat.
It produces sweat. Now what does that do for us? Besides give you a glow. What does it do? Why do we sweat?
To cool us down.
To cool us down. Good. So it helps with temperature, body temperature regulation. Oh, there's that concept of homeostasis again, right? We want to keep our temperature within a certain range, right? Damon.
Can you protect you from the outside?
Yeah. Protect you from the outside world, right? So, you know, I can, look, I'm not bleeding. Right? Pretty cool. underneath. So it protects us from mechanical trauma, right? Physical injury is mechanical trauma. What else does skin do? What other kinds of things does it protect us from besides physical injury or mechanical trauma? Bacteria? Yeah, so bacteria, infection. In fact, your skin is your #1 barrier against infection. Right? So when you see a guy come in and he has a big old abscess, big old infection in the skin, usually because he's got a little something there and picked at, right? And need an opening in the skin. And then bacteria can get in. Good. What else does the skin protect us against? What? Absolutely. So UV radiation, UV light, sunlight. So we don't fry when we go out in the sun. Some of us still do. We'll talk about that too today. What else does it protect us from? You might remember that we're water-based organisms, right? So we're like more than 70% made out of water. And so if we didn't have that waterproof covering, right, that keratinized certified skin epithelium, not only could water get into us, but we could dry out. Okay, we got to stay juicy on the inside. So skin also protects us from moisture loss. Good. Any other ideas of what skin does for us?
Hair follicles?
What?
Hair follicles?
Yes, we do have hair follicles, which make us look fabulous. But our hair is not nearly as functional as that of other animals, right? Of other mammals, especially. We've lost most of our hair, which would come really handy in Wisconsin in the winter. So it's really kind of too bad. Our hair doesn't, we have it, it doesn't do a whole lot for us as other animals today. It helps provide us information about our environment. Sensation. We have all kinds of sensory receptors in our skin to give us information about our outside environment. Texture, touch, pressure, temperature, pain, right? Put your hand on a hot stove. That's a really important piece of information. Okay? All right, let's see how we did. So protection from physical trauma, right? Physical injury, mechanical trauma. From invasion by germs, right? So protection from infection. Protect us from water loss and protect us from UV radiation, which we get from sunlight. In fact, these protective functions of skin are so important that if you lose a significant amount of your skin, so this is a person who's in a burn ICU, they've had significant burns to much of the surface area of their skin, the mortality rate is really high. So even with all the best medical care in the world, your water loss, your risk of infection is so high. These are mortality rates based on what percentage of your surface area of your skin has been burned away. You can see if you've lost about half of the surface of your skin, no matter what we do, right? Despite the best care, 25 to 37% of those people will not survive. That's how important our skin is. Right? You need to stay juicy on the inside. You need to stay protected from infections. All right, so we got the protective functions, and we got the regulation of body temperature through sweating. That's the one that's kind of the most obvious to us, right? We can totally experience that. But there are a couple of other ways that skin helps. So one is that the deepest layer of skin has a layer of adipose tissue. And you might remember that adipose tissue serves as an insulator. So our skin helps insulate us, right? You are sitting in a room that is, 70 degrees. That's colder than your body temperature, but you're fine, right? We have that insulation layer that helps maintain our body temperature. We can also regulate temperature of our body through blood flow to the skin. Okay? So what happens if you get really cold? Your extremities go numb. Your extremities go numb, right? So if you get really chilled, your hands get cold, your feet get cold, your nose gets cold. What your body is doing in this situation is sending less blood flow to these parts of your body. Because any time you send warmth out there, some of it's going to be lost through radiation to the outside environment, right? So you want to keep it in, right? It's like in your house, if you have horsehair heat, and you want to make, and it's like, you want these really, really super cold days, and so you want to just try to keep the heat conserved and concentrated in certain parts of the house, and you close the vents in other rooms and just close the doors, right? You stop sending heat to those places so that you can conserve it and keep it concentrated in the most important places, which are inside your head and inside your torso and abdomen. Yeah.
So it's different in men versus women, correct? Because I heard that like men's blood vessels typically flow or are positioned closer to the skin, and then women have it typically closer to their core, and that's why girlfriends always feel with
between
women.
men and women in their skin is really interesting. So in male-bodied people who have a lot of testosterone in their system, they tend to have less adipose tissue in that deep layer of the skin. So their blood vessels are less insulated. And so that's why their veins look closer to the surface of the skin. They aren't really closer, they're just less padded by adipose tissue. It is also what happens as people age, is you lose some of that adipose layer, which is why my veins are a lot more prominent than yours are. And some of these places, okay. All right, so we will decrease blood flow to the skin in order to conserve heat. And if we're too hot, we will do the opposite. Right? So here's some people from the local CrossFit gym after a competition. And you notice how kind of reddish they look? Right? That's not how they normally look. This is the best picture. Right? That's not how they normally look. When you exercise and you get really hot, or you get really hot for some other reason, like maybe you spent too long in a hot tub or a sauna, right? Your skin flushes. You send more blood to the surface of your skin to try to get rid of that excess heat. Right? So blood vessels can help us in each direction in terms of how much blood we allow to go to the surface of our bodies, or we keep it close in. Finally, of course, we can sweat. So, secreting fluid to the surface of the body, which then evaporates, and you get evaporative heat loss, right? So sweat is really, really useful, but it's most effective when what environmental condition is true?
It's hotter on the outside.
Absolutely, if it's hotter on the outside. Have you ever heard people when they talk about like Arizona or New Mexico, they're like, but it's dry, right? That's true, right? So you're going to be able to evaporate more effectively if the air is dry. If the air is very humid, like in a Wisconsin summer, that's when it's not evaporating, right? It's sitting there, and it's really miserable. So sweating is really effective when it's not super humid out, but if it's super humid out, it's not going to help you very much. It's not going to evaporate. There's too much water in the atmosphere anyway. Okay. This is the one we didn't get, right? Sensory receptors. So our skin gives us all this interesting information about the outside world. We have separate types of receptors for pain, temperature, fine touch, pressure, right? All these different things. So this is one of the ways that we learn about our environment. So skin is a lot of really cool things. I like my skin. The other one that we didn't get is it makes a vitamin for us. How crazy is this? Skin produces vitamin D in response to sunlight. Weird. It's almost like we're plants, right? We turn sunlight into something that we need to live. So cool. All right. So skin protects us from a lot of things, helps us regulate our temperature, gives us sensory information, and it makes vitamin D. Okay. What is the structure? Right? What are the parts of skin? How do they do these things? What does it look like under the microscope? I'm glad you asked. Okay. So we have three different layers. The top one is called the epidermis. Epi as a prefix means above or outside of. The middle one is called the dermis, lowest layer is called either the subcutaneous layer or the hypodermis. Hypo. You might remember the prefix in less than or underneath. Hypodermis. I like that term because it kind of fits with the whole dermis thing. So epidermis, dermis, and hypodermis. Here's another layer, another diagram, right? Hypodermis. And we're going to take a look at all these structures that we're going to find in each of those three layers. Epidermis is an old friend. So the epidermis, that topmost layer of the skin, is made of keratinized stratified squamous epithelium. So what we're seeing, here's that basement membrane, lots and lots of layers of cells that get flat towards the top. They start producing keratin, which is a protein, which then they leave behind as they die. And that keratin is what is the difference between our skin and the inside of our cheek. Right? That's this plain stratified squamous epithelium that has keratin on it. Right? So this is what is protecting us against water, so gain or loss, right? Helping keep us from drying out and becoming more raisins, as well as helps prevent physical injury from mechanical trauma. So there's the epidermis. We've seen that before. There's some cool features of the epidermis that we haven't learned about before. One is called a melanocyte. So you might remember cyte as a suffix means cell. Melano refers to melanin, which is a pigment. So these melanocytes live at the bottom of this layer of the keratinized stratified squamous epithelium, and they make melanin, which is the pigment in our skin. Now, as you might remember, those cells, as they mature, they move up as new cells are made underneath them. So the cells take up the pigment from the nearby melanocyte, and then as they move up the layers, they take that pigment with them. Right? It's like you had everybody lined up, and you give everybody a sheet as they, walk by you, and everybody has a sheet as they get to the top. Right? So the melanin then is what's going to give us that protection from UV radiation, from UV light from the sun. That pigment is going to absorb radiation so that it doesn't penetrate down into the skin and burn us. Pretty cool. So some of us have more melanin than other people. And a lot of times people say, oh, it must be that you have more melanocytes. And actually it's not. The difference in our skin pigmentation has to do basically with how hardworking or how lazy your melanocytes are. We all have approximately the same number of them. So people with more deeply pigmented skin, their melanocytes take the job very seriously, and they produce a lot of melanin. And they are very well protected from UV radiation. They may not even need to use sunscreen very much, if at all. So they are very well adapted to an environment where there's lots of UV radiation. People whose melanocytes don't take a lot of pigment, that lazy melanocyte, they can burn really easily. Right. Yeah, absolutely. So it's a trade-off. So I know you didn't all hear that. So if less UV can get through the skin, good, then less likely to burn. However, I need UV in order to make vitamin D. So it's a trade-off. So what we'll see is that a lot of times people whose ancestors came from parts of the world where there's a lot of sun have more deeply pigmented skin. It makes sense. They need more protection. People whose ancestors came from places that were really cloudy or far from the equator where you don't get good penetration of the UVB wavelengths that you need to make vitamin D, they tended to evolve to have less pigment. They needed to get whatever UV radiation they could in order to make enough vitamin D. That's how we have people with all different types of skin pigmentation, which is so cool. tanning is, right? So if you get exposed to UV radiation, then your melanocytes are going to be like, whoa, I guess I better get a little bit busier. They're going to make more melanin. Take a day or two, depends, right? A few days, and then you'll get a tan. That's how tanning works. If you're exposed to too much UV radiation too fast for the amount of pigment you have, or for the rate at which you can produce sufficient pigment, then you're going to burn, right? And some people, like, they can't tolerate much UV exposure at all, right? So you probably all know somebody who, like they just look at the sun for 2 seconds and, well, no, you shouldn't look at the sun, right? But they walk outside for 2 seconds and they get burned. All right? So that is what happens with too much UV exposure in the acute setting, right, over a short period of time. Exposure to UV radiation not only can cause a burn in the short term, but it can cause 2 problems long term. So chronic long-term exposure to UV radiation can cause 2 problems. Yes?
Skin cancer.
Absolutely. So skin cancer is one of them. Let's talk about why. Cancer is almost always due to a genetic mutation, either inherited or one that occurs in them. When UV rays penetrate down too far into the skin, they cause changes to DNA. That UV radiation causes genetic mutations. Now we have systems in our body to kind of like catch that and fix it, you know. But if enough of this happens over time, or if you're just really unlucky, then you can get a skin cancer from it. Right? So that's why the dermatologists are always like, use your sunscreen, right? The people whose job it is to take off skin cancers, use your sunscreen, right? So they saw the people who didn't and ended up getting skin cancer from it. The other thing that can happen, which is really interesting, is photoaging. It's called photoaging because this is due to UV exposure. You might think, well, this is just aging. Wrinkles just happen. Actually, they don't that much. So for the most part, and there are exceptions, but for the most part, wrinkles happen due to damage of the deep structures in the skin from chronic UV exposure over time. So that in the dermis of the skin, which we'll get to later, we have collagen fibers. And if they get damaged from UV radiation, you get wrinkles. So now obviously this woman is older than this woman, but I can also tell you this woman has been in the sun a lot more than this woman. This woman has actually been very good about sunscreen, possibly because she has to, because without it she'll burn. Right? So definite difference. But of course, we can't just spend all day indoors, right? It wouldn't be healthy for us because again, that flip side, we need sun exposure in order to produce vitamin D. Yeah.
So I know there are those lamps that people can get where it's like it simulates sunlight for seasonal depression, but that doesn't actually send out UV rays, correct?
Right. So light is on the electromagnetic spectrum, right? So it's a type of radiation. We have the total spectrum depending on wavelength. So depending on the light, some of those mood lights will actually give you UVB radiation, so you can make vitamin D from them. And some of them won't. There's a lot of difference from one lamp to another, you know, if it's a $10 one or a $150 one, right? Now obviously the lamps in the tanning salon are giving you UVB and UVA, right? So yeah, it depends. Good question. So we need to make vitamin D. This happens also in epidermis. You might have lost track, but we're still talking about epidermis. All right. So what happens is sunlight on the skin will cause the cells in the epidermis to take a cholesterol molecule. This is one of the reasons why it's important that you have cholesterol, not too much, but you need some, and turn it into vitamin D, which you can see is a steroid hormone. You might remember steroids have these rings. They're one of the having enough vitamin D is super important for bone health, because without it, you can't regulate calcium properly, and your bones end up too soft. So I was going to come back to this, but we're already brought it up. Slides ahead, right? So, with melanocytes, it's a trade-off. You have more pigment, you're better protected from UV radiation, but it can be harder to make vitamin D. You have less pigment, you burn easy, right? And higher risk of skin cancer, but it's easier to make vitamin D. Thank goodness you can also get vitamin D from other sources. Because most of us are vitamin D deficient by the time February rolls around. No matter what, our skin pigmentation is low. Alright, so far, we talked about the functions of skin, and we talked about the epidermis, in terms of it being that most superficial layer that's made of keratinized stratified squamous epithelium. We have melanocytes that make the pigment melanin, and it produces vitamin D. So now we're going to move to the dermis. So this is that middle layer. And look at all these things that are happening in the dermis. It's huge, and it's very busy. So there's lots of structures in the dermis, so we're going to spend a bit of time talking about this now. First of all this pink stuff that you see here, peachish stuff here, that is dense, irregular connective tissue, our friend from last time. So our specialized cells are fibroblasts, and the pinkish purplish stuff that you're seeing here are collagen fibers, and they're going every which way so that we get strength in multiple directions, right? This is leather, remember? Very strong in multiple different directions. So our dermis, the background tissue that all these other things are going to be in, is dense, irregular connective tissue. Okay. Then we have the associated organs. Okay, so these are the accessories of skin that work together with skin to form the integumentary system. So, hair follicles, right? So here's the hair, and then there's a little sheath of cells that surrounds it called the hair follicle, and that's where the hair is produced. In humans, our hair is not very functional. Our most functional hair that we have is our eyebrows, because they help prevent stuff from falling into our eyes, and our eyelashes. Aside from that, the rest of our hair is not very functional. Well, pubic hair helps keep things that are annoying out of your genital hair. So that's somewhat functional. But then, associated with the hair follicles, we have two other interesting structures. This little muscle here attaches from the side of the hair follicle up to the epidermis. It's smooth muscle, so that means it's involuntary, right? It's not like you can be like, oh, I'm going to squeeze my rectus muscles, right? You can't do that. What happens when these muscles contract? What's that cause?
Goosebumps.
Yeah, goosebumps, right? So, you know, you're like, why did we evolve that? Like, what good are goosebumps? And in us who have, like, no fur and no hair, not much, right? It's embarrassing. But if I were my cat, right, and then all the hair stands on end, right, that can provide two functions. It can intimidate a potential attacker by making you look bigger, and it can help trap heat and serve as an extra insulating strategy. So, but again, our hair is so sparse that it's just like, it's like having a tailbone. It's like, it doesn't really do anything good anymore. All right, so that's the erectopathy muscle, smooth muscle. And then we have a gland, which is going to produce sebum, so it's called the sebaceous gland. It produces an oily substance called sebum into the hair follicle, so that it can kind of come out in that little opening where the hairs come out from the surface of your skin. And that's your natural moisturizer. Okay, so your sebaceous gland produces natural moisturizer for the skin, which is good. Right? Keep it nice and supple. Okay? Yeah.
This might not be true, but I heard that like sebum is what causes a lot of acne.
Sebum is also what causes acne. right? So again, right, flip side and flop side. There's good and bad, right? There's a trade-off here. You want to have enough sebum so that your skin is nice and smooth and supple and doesn't get all dry and flaky and cracked, because then that's risk for penetration by infection and stuff, right? And it's not protecting you well. But if it's too oily and greasy, right, then you hurt. Absolutely. So at the end of the slides for today, there is some optional information about acne that I'm not supposed to be responsible for, but it's there. So I want to know about it. Kind of cool. All right. Other accessories, other organs that we have in the skin that work with the skin to form the integumentary system, the sweat glands themselves, right? So we're going to produce sweat to help lose heat. So in the dermis, so I like this image because they got rid of a lot of the other structures. They just simplified it. So there's the hair follicle with the sebaceous gland. They left out the erector-piling muscle. And here's the sweat gland. Sweat glands are interesting. They're these little tubes that then go into like a balled up tube. And the balled up tube part is like almost like a ball of yarn. And if you slice through it and look at it under a microscope, you'll see that this is an old friend too. This is simple cuboidal epithelium, which when we learned about simple cuboidal epithelium, we learned it's often part of glands, like the thyroid gland and the sweat glands, right? So that's what's lining the inside of this coiled up tube, and that's going to produce sweat. It goes into the inside, or lumen is what it's called, of the tube, and then it's going to release it out onto the surface of the skin. So you know when people talk about pores? We have a couple kind of openings in the skin. So we have two kinds. We have an opening for the sweat gland, or the sweat pore, and then we have an opening for the hair follicles. So we have two different types of openings. If you look really closely with magnification and the surface of the skin, you can see two different types. So there's our sweat gland. Also in the dermis, we're going to find blood vessels. So we already talked about the fact that these blood vessels, by sending more or less blood to the surface of the body in our skin, will help us regulate temperature. Okay? Send more blood if you want to get rid of heat, send less blood if you want to conserve heat. But of course, blood for the skin, just like for every other organ, serves as a delivery and transport service. So blood is bringing to the tissues nutrients and oxygen. So it's bringing oxygen and nutrients to the skin. And then, of course, the skin cells and all these other cells are also producing waste products, including carbon dioxide. And so the blood is also going to take those waste products and carbon dioxide away from the skin. Okay? That's what our circulatory system does for us, right? Drops things off, picks up things we don't want anymore, right? Delivers what we need, takes away what we want. All right. So dermis is also where you can find blood vessels. Finally, there's a lot going on in the blood. We have nerve endings. Okay? So we talked about the sensory function of skin. There are all different types of nerve endings for different types of sensation, whether it's pain or temperature or fine touch or pressure. I don't want you to waste your time memorizing those things, because you'll forget it in a week. That won't be any good. Right? But just know we have different types of nerve endings, different types of nerve receptors for different types of sensation. In fact, it's possible to have certain types of injuries to your nervous system where you lose the ability to sense pain, but you can still sense touch, or vice versa. In fact, if you've ever gotten stitches and they gave you numbing medicine, it's possible, if they gave you just the right amount, that then when they stitched you up, it didn't hurt, but you could still feel touching. That's because those are different types of nerve endings. And it takes a lot more lidocaine to deaden the one than a touch. Okay? We have different types of nerve endings for different types of sensations. Cool. All right. There's all the dermis together, right? We've got our hair follicles with our hair going every which way. Last layer, hypodermis, subcutaneous layer. That means that there's underneath cutaneous skin. So hypodermis, not much to, which is pretty nice. So it's mostly adipose tissue. There's some loose areolar connective tissue to help hold the skin on our body. And again, if you've ever skinned a deer, it's not that hard to pull the skin out. Right? You remember that loose areolar connective tissue is that crab bone stuff. That's what holds our skin onto the rest of our body. And we're going to have some larger blood vessels, which are the feeders for those smaller ones that go up into the dermis. So if you get a cut that goes all the way down into hypodermis, it's going to bleed more than a cut that just goes down into the dermis, where there's smaller blood vessels. And of course, if you get a cut that only goes through the epidermis, you won't bleed at all, because there's no blood vessels there. Right? So if you ever had a friend that did that thing where they took pins and put them through the end of their fingers, right? If you just do it through the hypodermis, it doesn't, the epidermis, it doesn't hurt because there's no nerve endings there. It doesn't bleed. There's no blood vessels there. But still, I don't recommend it. Yeah.
So is the reason why head wounds bleed so much because it's overall just a thinner layer of everything?
So head wounds bleed like crazy because we have a lot more blood vessels on the head. A lot more densely packed blood vessels in the head than we do almost anywhere else. Yeah. So they always look worse than they are. They just bleed a ton, and then it turns out it's not that big of a cut after all. Yeah. If you want to cut yourself, look back here. Cutting blood up here. Back here. That's what we have. All right. Not a lot going on here. Skin in the face and head got hair. Alright, so I'm going to show you an image of the hypodermis and someone who had a significant injury. And it's kind of bloody. I'm sorry, I looked for an image that was not this bloody, of from a surgery or something that would have been better, and I couldn't find one. And searching for these things on Google Images. Alright, so you don't want to see it? Don't look. There we go. So here's the skin. All this adipose tissue, this yellow stuff, that's the hypodermis. That's that subcutaneous layer, that's subcutaneous fat. This injury is really deep. You're in the operating room right now. This is bone down here. These are muscles. And I'm making it go away now. Okay. Moving on.
Yeah, I think so.
Yeah.
Was that his arm or what?
Oh, that was somebody's forearm. Yeah. This is what skin looks like under the microscope. Epidermis here, which is our keratinized stratified squamous epithelium. Here's our dermis, which is our dense, irregular connective tissue with hair follicles, sebaceous glands, erector piling muscle, and sweat glands. Down here is the hypodermis, mostly adipose tissue. Remember, it looks kind of like chicken wire. Mostly adipose tissue. This is review, but what I want to point out is all the different tissue types that we found in skin. So, right, the epidermis is that keratinized stratified squamous epithelium, and in the dermis, we have that dense regular connective tissue. The sheath of the hair follicle itself is epithelium. The erector piling muscle is smooth muscle. Sebaceous glands and sweat glands are both made out of cuboidal epithelium. Nerves are nervous tissue. And blood vessels, which we haven't talked about how they're constructed yet, but they're constructed of epithelium, muscular tissue, and connective tissue. And then the hypodermis, right, has that loose areolar connective tissue and adipose tissue. So we have all these different tissue types working together to form an organ, and different organs working together to form an organ. Let's see how we do. Yes, Megan. How do how does what happen? Ingrown hair versus layers of hair. Oh, ingrown hair. That's really good. Oh, I'm recording, so I can't go backwards. Oh, so sometimes when you shave a hair, or if you pluck a hair, right, that dermal layer will seal over, and then the hair can't get through. That's what causes an ingrown hair. Yes, good question. They are pesky. All right.
Okay, so moving on to organ systems and homeostasis. So remember at the beginning of the lecture, we talked about all of the different organ systems that we have, and here they are represented again. And it's really important to remember that all of these organ systems are going to work together to maintain lots of different variables within a specific range. So keep things in balance for us as humans so that we can continue to function. So this, of course, is what we call homeostasis, right? Maintaining certain variables within a specific range to allow for optimal function or function at all. Because if you go too far outside that normal range, things start breaking down and not working. So there are lots of things that we have to regulate and keep within a very specific range as human beings. So we've already talked about temperature regulation. So we do pretty fine between about 96 and 100 degrees Fahrenheit. Anything cooler than that or warmer than that, and systems start not functioning properly. pH, right? How acidic or basic or alkaline the substance is. So our blood pH is normally about 7.4. If it gets much outside of that normal range, we start having problems. The body doesn't work properly. We also, due to osmosis, need to maintain appropriate concentrations of things. So not only do we need to have the right amount of sodium or glucose available in our bloodstream, it also has to not be too concentrated or not concentrated enough, right? So if we have a hypertonic solution, if our blood is hypertonic, then our cells might crenate as water moves out of cells into the blood. Or on the opposite side of things, if we have a hypotonic solution, if the blood is too dilute, then water will move into the cells and they could swell and possibly burst or lyse. We also have to maintain our overall fluid volume so that we keep our blood vessels full and maintain that pressure in those blood vessels so that we can send that blood to all the different parts of our body. Oxygen and carbon dioxide are two gases whose levels we have to control very precisely. We have to make sure we have enough oxygen at all times. We have to make sure we have not too much carbon dioxide, but just enough at all times. And so all these organ systems are going to contribute to this. Now, in order to maintain this balance, somebody has to be in charge. So we have control centers. And the two main control centers that we have in our body for homeostasis are these two, the nervous system and the endocrine system. So the nervous system, which is our brain, spinal cord, and our nerves. Our nervous system is really good for quick, rapid responses to things. We can send a nerve impulse in less than a second, just a fraction of a second. So our immediate short-term responses to things are going to often be mediated by the nervous system. But we also have the endocrine system. So the endocrine system is that system of glands, of which there are several different types that are located throughout the body that produce hormones. Hormones travel through the bloodstream. So this is a system that takes a bit longer to kick into gear. It's slower to respond, but it's going to provide a more sustained response. So those are the two main systems that are going to regulate and be our control centers for homeostasis. In order to maintain things within a very narrow range, we tend to use what are called negative feedback systems. And so the way a negative feedback system works is just like the thermostat in your house. So I know this is an old-fashioned one, right? But so a thermostat in your house, say you set it for 65 degrees. So you want your house to be, in general, pretty close to 65 degrees. What will happen is if the temperature starts dropping below 65, say if it gets down to 63 degrees, first of all, there's a sensor in that thermostat that's measuring the temperature. It's sensing the temperature. So your sensor is going to say, uh-oh, and then it's going to send a signal. So it's going to be a controller. It's going to send a signal to your furnace, and it's going to tell the furnace to turn on. And your furnace then is going to turn on and generate heat and blow it throughout the house. As it does so, the temperature in the house is going to gradually increase. It'll get up to 65, and your thermostat will usually let it get a couple degrees above 65, say 67, and then the thermostat says, okay, that's good enough. And so then it's going to, again, sense that increased temperature and turn off the signal to the furnace. So that's what we call a negative feedback system. It turns off when you've kind of gotten above or just above the level that you want to be at. So the furnace turns off, and then gradually then over time the house cools down a bit until it gets down to 63, and then the thermostat senses that, sends a signal to the furnace turns on again, and the whole cycle repeats. So what we see is that temperature in your house is not always exactly 65, and so I'll just use my little cursor here, right? So if let me use blue. So if this is 65, I can't draw a line very well, and the temperature gets below that, right? We turn on the furnace, and then the temperature comes up, and then once it gets a bit above that, we turn the furnace off, and it gradually drifts down again, and we turn the furnace on, turn the furnace off. And so what you see is these gradual, slow fluctuations that are kept within a pretty narrow range, right? So between, say, for this example, 63 and 67 degrees Fahrenheit. So negative feedback mechanisms are really good for keeping something within a narrow range. The opposite of a negative feedback system is a positive feedback system. So positive feedbacks do not keep something within a narrow range. Positive feedback systems will actually have something build and build and build and get bigger until eventually it bursts, right? So eventually something explosive happens. We don't use positive feedback mechanisms very much in the body at all because we're usually trying to maintain homeostasis, and that's not what these do. These do not maintain the status quo. They result in a significant change. So two of the best recognized examples of this positive feedback mechanism would be ejaculation in the male, right? Things build, 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 and then kind of explode, right? And the semen gets expelled from the body. That is not maintaining the status quo. That's a significant change. And childbirth. So you have labor starts with a mild contraction of the uterus, trying to push on the baby, and then that gradually builds into stronger and stronger and more forceful contractions until eventually the baby gets pushed out, right? So something builds, 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 builds until something that happens that changes the status quo, often something quite significant or explosive. So again, positive feedback mechanisms exist. We don't use them very much in our body because usually we're trying to maintain homeostasis. So if we look at the example of temperature regulation, since we've talked about that today in regard to how the skin contributes, right? Let's look at how we control that in the body. So the control center and the sensor for temperature regulation in humans is the hypothalamus, which you can see here is a part of the brain. We're looking at the brain here. It happens to be located underneath the thalamus, hence the name hypothalamus. And so it's going to sense body temperature, and it's also going to be the control center that'll send out a signal if we need to do something different. So if our body is too cold, as we discussed earlier, we're going to decrease blood flow to the surface of the skin because we want to conserve heat. So the hypothalamus will send signals down through the spinal cord, out through the nerves to the blood vessels in the skin to tell them to constrict, to tighten up, and close down a bit so that less blood flows to the skin. If we're really cold, the hypothalamus will also send nerve signals down to the skeletal muscles, to our muscles, and that will cause us to shiver. And that muscle contraction, that muscular work, will generate heat, right? Just like when you exercise, a lot of muscular work generates heat. So we're trying to do things to conserve heat and build body heat to get back up to the normal temperature. If our body is too hot on the converse side, right, we're going to do things we've already talked about. So the hypothalamus is going to send nerve signals out to the sweat glands and tell them to produce sweat so we can hopefully lose heat through evaporative heat loss. Hopefully that sweat will evaporate off our skin. We'll also again signal those blood vessels to open up and dilate and send more blood to the surface of the body, to the surface of the skin, to try to get rid of heat that way. So the hypothalamus is both the sensor and the control center for temperature regulation in the human. And so this is really important, and we do this all the time. That's why we are warm-blooded animals. We usually are about 98.6, so there's lots of individual variation from person to person. And so we can withstand a lot of different types of environments, but there are limits, right? So if you are exposed to something that is too hot and too warm, it can exceed your body's capacity to adjust and accommodate that, right? If it's too hot and humid out so that your sweat is no longer evaporating when you sweat, you can get overheated. If you don't have enough fluid in your body, if you're super dehydrated and you can't sweat anymore because you've already sweat all your fluid out, you can get overheated, right? So then if you're getting overheated, you're not maintaining homeostasis and your body starts to malfunction. So you can get heat stroke. You can even die from getting too hot, which is called hyperthermia. On the other side, right, you can also die from getting too cold, hypothermia. There's a limit to what, reducing blood flow to the surface of the body and shivering can do for you. There's only so far it can take you. So if the environment is too extreme, you can get hypothermia and you can start to have malfunction of lots of different systems in your body. Including the nervous system, including your heart, which is part of your cardiovascular system, and it can get severe enough that you can die. So here's some data about heat-related deaths, right? So they tend to be more common in male-bodied people, not because their bodies work all that differently than female-bodied people, but because they tend to engage in different types of activities than female-bodied people, just kind of culturally. So a lot more athletic activities, more likely to do football or things where they're wearing a lot of pads and helmets. Also a little bit more likely to try to power through something rather than take a break if they're starting to feel unwell. So culture is important too here. This is getting to be really important when we think about how our world is changing and our climate especially. So many areas of the world, if not most of them, are getting hotter over time. And it's gotten to the point now where there are some places that are literally becoming too hot for humans to live there. So we already have some places like that. So like Death Valley in California, for example, aptly named, right? People cannot survive there without significant environmental controls. Certainly if you live in a completely air-conditioned building, you would be fine. But you can't really live there otherwise. And so one of the things that's interesting about humans' ability to respond and adapt and cope with heat is our ability for the sweat to evaporate. So there's this thing called wet bulb temperature, and it gives you a measurement of not only what the temperature is, but how humid is it, right? Because if it's super humid, then the sweat just won't evaporate because the air is already laden with moisture. So it's named a wet bulb temperature because literally when they first started measuring this, they would take one of the old-fashioned thermometers and put a wet cloth over the bulb part. And then, of course, if it was dry enough out that evaporation could happen, then the temperature on the thermometer would be lower. But if it was really humid and evaporation wasn't happening, the temperature would be higher. And so what we know for humans is if the wet bulb temperature is higher than 35 degrees Celsius, so this is Celsius, right? So human body temperature is 37 degrees Celsius is normal body temperature. So 35 degrees Celsius is in the low 90s. Right? So if the wet bulb temperature is in the low 90s, even if you're just sitting outside doing nothing, if you sit in that kind of weather for long enough, you will die, right? So just sitting there is enough to kill you, right? That's so hot that you cannot survive. Now in Wisconsin, we're a little bit more familiar with the opposite. We're a little bit more familiar with the fact that there are certain days in January or February where if you sat outside for a period of time, you would die, right? It's so cold that the human cannot survive. You cannot adapt to that. But given the changing climate, this change in heat and places becoming hotter is becoming more and more of a problem. And we're breaking records, and there are becoming more and more places in the world that are just not going to be habitable by humans unless they just kind of live inside all of the time and never go outside. In fact, there's a place in Vietnam where it's gotten so hot and humid that they literally cannot farm during the day, because they will get heat stroke. It is just too hot and too humid. Usually, in the story they're talking about by 8, 9 o'clock in the morning, it's already too hot and humid to do any physical work. So, because of course, when you do physical work, your muscles generate heat. So instead now they have had to take into planting and doing their rice farming in the dark at night, because it's a little bit cooler, of course, at night, and that's the only time that it's physically safe for them to be doing work outside. So this is becoming a real problem, actually, in many areas of the world. So the thing about homeostasis, right, is to remember that we use negative feedback mechanisms to maintain certain variables within a narrow specified range of kind of our optimal ranges for human functioning, but that if there is a significant challenge to our ability to do that because the environmental circumstances are too extreme, right, we're going to run up against a limit, and illness or even death can result. So let's just think through a couple of questions here. So let's say you eat a really salty meal, okay? So you go to McDonald's or something, you eat a really salty meal, and so that's going to make your blood sodium level get really high. So think about what happens if you eat something really salty, a whole huge bag of popcorn. Well, what's going to happen is you tend to get thirsty. And those are the homeostatic mechanisms in your brain stimulating a sense of thirst, right? That's your hypothalamus again, stimulates thirst, so that you're going to go drink some water. And then that water, which you will absorb, because you absorb everything that you eat if you can, that water is going to dilute out that sodium, get your tonicity level, your sodium concentration level back to normal, right? So that's pretty cool, right? It's just going to make you thirsty, so you will water down that salt that you just ingested, ate, and absorbed. Similarly, right, if it's a really hot day, you've been exercising, you've been sweating a lot, your body is dehydrated, you're low on water, same thing, right? You're going to feel thirsty. So your brain is going to trigger thirst so that you will take in water to maintain that homeostasis and maintain that fluid volume. Let's do one that's a little different. Let's say you move someplace that's really high altitude, like Aspen, Colorado, 8,000 feet above sea level. So there's less atmospheric oxygen present there. There's less oxygen basically in the air. So what's going to happen? Well, right away, your nervous system is going to automatically maintain homeostasis by causing you to breathe faster. So you will breathe faster, not even intentionally, right? This is going to happen automatically, thankfully. And you will breathe more quickly so that way you can still get in the same amount of oxygen that you need to, because you're just taking in more air in any given minute. And that's what will happen as a result of your nervous system acting right away. Long term, if you stay at altitude, your endocrine system is actually going to get involved, and you're going to start making a hormone that will cause you to make more red blood cells, which are the cells that carry oxygen, so that you get really good at delivering oxygen to the parts of your body that need it. So you can have an endocrine system response to maintain homeostasis in terms of oxygen delivery to the tissues. And that will take longer to kick in, but then it will also last longer. So that's another example of how the nervous system usually does the immediate short-term things, but then the endocrine system can do longer, more sustained things over time. So this is the summary of our lecture from today. So we talked about organs that work together as organ systems using the integumentary system as an example. And we talked about the functions of skin and the different structures, the 3 different layers of the skin. And then for homeostasis, all the organ systems are going to work together to help maintain this in all the different ways that we need to keep things at the status quo. And the nervous system and the endocrine system are our control centers for homeostasis. And we're going to use negative feedback systems because that's how we keep things within a narrow range. All right, that's it for today. Thanks, everybody.